Hey guys, we're going to take a look at section 3.4, and this talks about concavity and the second derivative test. So first of all, let me remind you that we did the first derivative test back in section 3.3. The first derivative test said that if you find the critical values of a continuous function, then if it goes from increasing to decreasing or positive to negative, then it's a max there. If it goes from decreasing to increasing, then it's a min. And then if it stays increasing to increasing or decreasing to decreasing, then it's not a max or a min. All right. Second derivative test is going to tell us something else, and the thing it's going to tell us about is this idea of concavity. So concavity is not a word that you have heard yet at this point in the year. So concavity is more like asking, is the graph curving up or is it curving down? All right, so that's really what concavity is about. So we're going to find those spots where it's, you know, kind of U-shaped facing up, or where it's, I can't do that well around my tripod, or U-shaped facing down. So concave down versus concave up. All right. So curving up like that, so that it's kind of, imagine if it's a cup, it's holding liquid here, and here we've just kind of dumped it out. So curving up or curving down. All right, so let f be a function that's differentiable on an open interval I. The graph of f is concave upward on I if its derivative is increasing on the interval. All right, so again, here its derivative would be increasing, its slope would be increasing, and it is concave down if it's decreasing on the interval. Now we're going to have a little bit of a better definition than this in just a second, but let's look at this graphically. How does this help us talk about concave up versus concave down? So it's saying let f be differentiable on an open interval. If the graph of f is concave upward on I, then the graph of f always lies above all of its tangent lines. So let me give you an example here. So let's say we have this curve right here, right? This is y, this is x, this is f. And if I take any point on here and I draw its tangent line, it falls under the graph of f, or f lies above it. Let me pick another one. All right, again, f lies above it. I can come up here and draw the tangent line, f lies above it. I could come over here, draw the tangent line, f lies above it. So this is concave up. And f is, I can't say it's increasing everywhere, but it is generally increasing right here. Right? Then let's draw a picture of concave down. So similar to what we just drew, but the opposite direction. So if we've got something like this, that's concave down, again, pointing down. So if I were to pick a point on here, all right, so it says let f be differentiable. The graph of f is concave down on I when the graph of f always lies below the tangent line. So let me draw a tangent line here. The graph of f lies below the tangent line here. The tangent line is above f, so f lies below it. We could continue to do that at all points on the graph of f in this interval. All right, so that's just kind of a loose idea. Again, it's concave up if it's pointing upward like that. But again, we could talk about the tangent lines all lying below the graph of f, or f lying above all the tangent lines, and same thing here in reverse. When it's concave down, all the tangent lines lie above f, or f lies below the tangent lines. All right, so Theorem 3.7 is the test for concavity. So if f is a function whose second derivative exists on an open interval I, then we'll say that if the second derivative is greater than 0 in this interval, then the graph of f is concave upward. So here we see that the first derivative talked about slope, and the second derivative is going to talk about concavity. All right, whether it's concave up or concave down. So if the second derivative is positive for all x in an interval, then the graph is concave up. And if the second derivative is less than 0 for all x in the interval, then the graph of f is concave down. If it's equal to 0 for all x in the interval, then f must have been linear. All right, because if we take the first derivative of a linear function, again, think of something like y equals negative 3x plus 7. We take the derivative of that, we would just get y prime equals negative 3. And if we take the second derivative and get 0, again, the only way we could do that is if we started with something that had been linear. All right, concavity is not defined for lines. In other words, a straight line is neither concave up or concave down. Again, a straight line isn't going to have that curving effect that, that a curve would. So, all right, to apply Theorem 3.7, the first thing that we need to do, again, this should start to sound oddly reminiscent of the first derivative test, or what we did for maximum and minimum, or increasing and decreasing. So to locate the x values for which the second derivative, I'm rushing here. To apply Theorem 3.7, find all the values for which the second derivative is 0 or the second derivative does not exist. All right. Next, we use these x intervals to determine these x values to determine test intervals. Same thing that we did before. Finally, test the sign of f double prime in each of the test intervals. All right, so again, it's very similar to what we were doing for first derivative to find the max and min, but this time we're doing it to find concavity. All right, so in example 1, we're going to determine the concavity of a function. I'm going to scooch this out of the way here, and we will go to this example. All right, so determine the open intervals on which the graph of 6 over x squared plus 3 is concave up or concave down. All right, so Theorem 3.7 says that the first thing we need to do is make sure that this function is continuous on a particular interval that we're going to work with. So if we look at this and we try to determine the continuity of it, actually the differentiability of it, so let's take a look at that. This is never going to be 0, because we've got something that is at a minimum 0, but generally positive, and then we're adding a positive number to it. So this is never going to be discontinuous. In fact, it is going to be differentiable everywhere, because we can just keep taking the derivative of it, and we'll never get something in the denominator that's going to give us a 0 in the denominator. So then that tells us that we need to find the second derivative of this. So the first derivative, this is where you're going to, this is going to be a problem, because taking the second derivative of all these functions tend to be a pain. All right, so I'm not going to use the quotient rule. I'm going to rewrite this as 6 times x squared plus 3 to the negative 1. All right, so when I take the derivative of that, that's going to give me negative 6 x squared plus 3. I decrease the power by 1, so it's negative 2. Then I take the derivative of the inside, that's 2x. All right, I'm going to just rewrite that as negative 12x times x squared plus 3 to the negative second power. Now it needs me to take the second derivative. I'm going to leave it in this form because I feel like it's going to be a little bit easier to take the second derivative of this than to use the quotient rule, which is what I would do if I put it back in this form, negative 12x over x squared plus 3 to the negative second power. All right, so I'm going to choose not to use that for right now for the derivative and use this instead. All right, so I take the derivative of this. Now I have to use the product rule. All right, so it's first times the derivative of the second. So the second is going to give me negative 2 times x squared plus 3 to the negative third power times the derivative of the inside, which is 2x, plus the second, that's this, x squared plus 3 to the negative 2 times the derivative of the first, which would be negative 12. All right, let's simplify that. I'm going to take all these little monomial clusters around and join them together. So I'm going to get, it's going to be positive because I have a negative times a negative. It's going to be 4 times 12, which is 48. And then it's going to be x times x, which is x squared. And then I've got this x squared plus 3 to the negative third. And then negative 12, we'll just make that minus 12 times x squared plus 3 to the negative second power. And the way that we were simplifying before is we said, let's get rid of all our negative exponents, so find the smallest of them, right? So negative 3, and then we'll multiply top and bottom by the positive version of that. So x squared plus 3 to the positive 3 over x squared plus 3 to the positive 3. When I do that, I get f double prime of x equals 48 x squared. When I multiply the top, this right here, when I distribute that in, that's going to wipe that out. The negative 3 and the positive 3 will cancel, giving it x squared plus 3 to the 0, which is just 1, minus 12. And then here, we're going to cancel out 2 of these, and we'll be left with one of them. So x squared plus 3. And then in the denominator, we get x squared plus 3 to the third power. I'm going to factor out a 12 here. So with that 12, I'm going to be left with 4x squared minus, I'm going to distribute the negative through here, so it's minus x squared minus 3 all over x squared plus 3 to the third. And let me cancel that, so I end up with 3x squared minus 3 over x squared plus 3 to the third. One more simplification and I'm going to say it's enough. I'm going to take a 3 out of there. So that becomes 36 x squared minus 1 over x squared plus 3 to the third. And in fact, I can do one more thing, which is factor that using difference of squares. So 36 x plus 1, x minus 1, all over x squared plus 3 to the third. Okay, so now we found the second derivative, and we need to find out where it's either 0 or it doesn't exist. All right, so again, we said this is never going to have a problem with not existing because the denominator's never able to be 0. So we just need to find where the derivative is 0. And that is going to occur when x equals 1 or when it's negative 1. So f double prime will equal 0 when x equals 1 or x equals negative 1. All right. I'm going to leave this space open and we'll come back in just a minute to draw a graph of it. But so then what it says to do next is to set up test intervals. So again, remember we did this in class the other day where we set up intervals. It was continuous everywhere. We're looking at where it's concave up and concave down on the entire real line. So I'm going to set up intervals that go from negative infinity to negative 1, from negative 1 to positive 1, and from positive 1 to infinity. Then I have to pick a test value in this interval. So I'm just going to pick x equals negative 2, x equals 0, and x equals positive 2. And then this asks us to find the sign of the second derivative. So again, I'm going to use this version of it. It's the most factored version that I have. So when I plug negative 2 in there, again, the 36 is always positive, so we don't have to worry about this. When I do negative 2 plus 1, I get a negative. I'm just going to write that down here, negative. When I do negative 2 here, I get another negative. And the bottom is always going to be positive. So I have negative times negative over positive, which is going to be positive. Right, I'll do the same thing for 0. When I plug 0 in here, I get 0 plus 1 is 1, that's positive. 0 minus 1 is negative, so positive times negative over something that's always positive, that's going to give me negative. And then I plug 2 in, 2 plus 1 is positive, 2 minus 1 is positive, that's always positive, so it's positive. All right, then the conclusion is that in this interval, it's always positive. Therefore, it's concave up. In this interval, it's always negative, so it's concave down. And in this interval, it's positive, so it's always concave up. All right, so let me sketch what it looks like so that you can see what we're talking about here. All right, at +1 and -1, something interesting happens. And that is, those are the spots where it changes concavity. So it looks something like this. These are not asymptotes. Please don't see them that way. It's just I want you to see that it goes something like this. Maybe you want to look in the book for a better example of what it looks like, because again, I'm not good at drawing these freehand. So it's saying from here, from -infinity up to -1, it's concave up. It's not quite as exaggerated as the pictures that I drew you before, but you can see that it has that upward slope, and then, or that upward curving. And then from -1 to +1, it switches to concave down. And then from +1 to +infinity, again, it's kind of curving upward there. All right, and it tells us down here, the function is an example of something that's continuous on the entire real line. If there are x values at which the function is not continuous, you also have to use those along with your points where the second derivative is 0 or where it isn't defined. Again, we saw that in one of our examples in 3.3. We can't skip the places where it's discontinuous. We have to add that to our table. So we're going to have an example of that now in example 2. All right, so example 2 has the function f of x equals x squared plus 1 over x squared minus 4. And again, they ask us the same question, or command us to do the same thing, say where it's concave up or concave down. So again, they kind of gave us a heads up that there would be something different about that in terms of the continuity. And we can tell just by looking at it here, x squared minus 4 definitely will be 0. This factor is using difference of squares, so it's x plus 2, x minus 2. So we can say that f is discontinuous at x equals plus or minus 2. It's not continuous, and then it's not differentiable. All right, so it's neither continuous nor differentiable at those two x values. All right, so then let's go on and do what Theorem 3.7 asks us to do. If we're trying to find places where it's concave up or concave down, the first thing we have to find out all places where f double prime of x equals 0, or all places where f double prime is not defined. All right, so let's start out with finding f prime of x first. And again, f was x squared plus 1 over x squared minus 4. So the first derivative of this is going to be bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. All right, let me clean that up a little bit. So actually, I'm going to pull out a 2x because both terms have that. So we'll have 2x, and then we've got what's left is x squared minus 4. After I pull out this 2x, I'm left with minus x squared plus 1. So I'm just going to distribute that minus sign. So it's minus x squared minus 1. And then we've got x squared minus 4 quantity squared. This cleans up nicely because these cancel out. So then we've got a negative 5 right here times that 2x. So f prime, let me just write it here just for space. I end up with negative 10x in the numerator and x squared minus 4 squared in the denominator. All right, now let's take the second derivative. So f double prime of x is the bottom. So x squared minus 4 squared times the derivative of the top, which is negative 10, minus the top, negative 10x, times the derivative of the bottom. We're going to have to use the chain rule here. So this is going to be 2 times x squared minus 4. Decrease the power by 1, so it goes to 1, and then take the derivative of the inside. And that is all over the bottom squared, which is x squared minus 4 to the 4th. Let's clean some stuff up here. I noticed that they both have a negative 10 in there, and they both have 1 x squared minus 4. So let's take those two factors out. So I'm going to take out a negative 10 and an x squared minus 4. I'm probably not going to have enough room to do this. What's left is an x squared minus 4. And then after I take out that negative 10 and the x squared minus 4, what's left here is this x, this 2, this 2x, and no x squared minus 4. So let's see. Oh, that's not going to be bad. So 2 times 2 is 4. X times x is x squared. This is gone, and that's gone. So it's minus 4x squared. All over x squared minus 4 to the 4th. Okay. I can cancel out one of these. So when I go to the next line, I'm only going to have 3 in the denominator. So I'm going to have negative 10. Then I'm going to do x squared minus 4x squared, which is going to give me negative 3x squared minus 4 all over x squared minus 4 to the 3rd power. I'm going to factor out the negative in here, or maybe I should just distribute the negative through here. Leave the 10 out there, but I end up getting 10 times 3x squared plus 4 all over x squared minus 4 to the 3rd power. All right, so that's our derivative. So we're wondering when the numerator is 0, because again, we're looking for where is the second derivative equal to 0. That's going to come from when the numerator is 0. If you look at that closely, you see there is no way that's ever going to be 0. If we couldn't tell just by looking at it, first of all, x squared will never be less than 0. It might be equal to 0, but it'll never be less than 0. So at a minimum, that's 0. We add 4 to it, so this is always going to be positive. And then multiplied by 10, that's still always positive. But if you didn't see that, you could just try and solve this. 3x squared plus 4 equals 0. Bring the 4 over, and we would get 3x squared equals negative 4. That would not work because that's going to give us imaginary solutions. All right, so there is no place, so f double prime never equals 0. And we already know about the places where the denominator is equal to 0 because those were not part of the domain. Those were the places where the function was discontinuous. So the two numbers that we're looking at are x equals positive 2 and negative 2. And that's those are gonna be the intervals for which we set up our test values here. So we're gonna go from negative infinity to negative 2. Negative 2 to positive 2, and positive 2 to infinity. Again, what's going to happen here is we have asymptotes, and they can end up chopping the graph up, and maybe in that entire section we'll have concave up or concave down. So again, if you want, you can draw those so that you can see that there's going to be asymptotes there on the graph. So you remember it's not just something like where the derivative doesn't exist, which would be a sharp point or something. Okay, so we pick our test value. I'm going to pick negative 3. And then here I'm going to pick 0. And here I'm going to pick 3. So then the sign of f double prime, again, I'm going to go back to my most factored form right here. I put in negative 3. And again, I don't have to worry about that. That's always positive. 10's always positive. So really, I'm just looking at the denominator. So I've got negative 3 squared is 9, 9 minus 4 is 5, 5 cubed is positive. So we end up with positive right here. I put in 0. Again, I'm not even going to check the top, that's always positive, but here I do 0 minus 4 is negative 4 cubed still stays negative. So this is negative. And then I put in 3. And again, if negative 3 worked, positive 3 is because Again, that denominator is an even function, so whatever it was in this test point, it's going to be the same sign in this test point. But let's just do it again. 3 squared is 9, minus 4 is 5, cube 5, we get positive. All right, so what can we conclude? We can conclude that in this interval, negative infinity to negative 2, it is always concave up. In this interval, negative 2 to positive 2, it's always concave down. And in this interval, positive 2 to positive infinity, it's always concave up. And let me show you what the graph looks like so you can see this. So we know that we've got vertical asymptotes at negative 2 and at positive 2. So it looks like this. It's concave down. Now, I have not done any test points with you, but I have on my own, so I can tell you that it looks something like this in here. Right, again, that we see as the concave, where it's concave down. And then on the sides right here, it does something like this, almost like a 1 over x kind of graph. All right, so again, we see the concave down and the 2 concave up. And again, we had to use the spots where there were discontinuities because there were no other points that showed up as being kind of those critical values that we talk about. All right, so let's talk about a point of inflection. It says let f be a function that's continuous on an open interval, and let c be some point in the interval. This is, again, the standard setup for us anymore. It says if the graph of f has a tangent line at the point c, comma, f of c, then this is a point of inflection of the graph of the point of inflection of the graph of f if the concavity changes from upward to downward or downward to upward at the point. Right? So it's saying that if f has a tangent line at that point, then there's a point of inflection there. It seems like the definition should be a little bit, I don't know, a little bit stronger than that. But anyway, so let's see what that looks like. Let's see if we have a picture in the book that I can draw for you. I don't have one in my notes. I'm in the wrong section. Hold on. Hold on. Okay, here we go. So, well, it's giving us a couple things right here. If the graph, if the tangent line exists at that point, then, all right, here's 3 different types of points of inflection. Let's draw this, all right? So let's say we had this graph that looks something like this, right? So we would be talking about some place like this, all right? Notice how it's concave up right here, and then it switches to concave down right here. That point is called the point of inflection. Right, it's telling us in the book that there are 3 different kinds of points of inflection. All right, here would be an example of another one. And actually, if we look at the tangent line, it looks like this. Right? Here would be a second type. Right? This would have a horizontal tangent line. Right? Notice that here, this is pointing downward. It's concave down. And here it's pointing up, concave up. So this point right here is also a point of inflection. Sometimes we abbreviate that when we're doing these as POI. I don't know that that's standard, but that's what we usually do. And then the third type is if we end up with a graph like this, right, where I might have a vertical tangent line. Right, again, here, concave up, concave down, that right here is the point of inflection. All right, so if it switches from concave up to concave down or concave down to concave up at that point, then it's a point of inflection. All right, so here is theorem 3.8. If c, f of c, is a point of inflection of the graph, then either the second derivative must have been 0 there, or it did not exist. All right, so if we've got a point of inflection, the only way that could have happened is if the second derivative was 0 or it did not exist there. Okay, let's look at an example of how to find a point of inflection. Okay, this is example 3. For some reason it got cut off. The heading did. It's on the bottom of the previous page. But determine the points of inflection and discuss the concavity of the graph of f of x equals x to the fourth minus 4x cubed. So again, the previous theorem, which was theorem 3.8, says that if something is a point of inflection, then it must have come from when f double prime was equal to 0 or f double prime does not exist. All right? It doesn't say that if f double prime is 0 or f double prime doesn't exist, then it's necessarily a point of inflection. It's just telling us that if we have a point of inflection, it must have come from this set of values. All right? So what we're going to do here then is find all these values and see if they are points of inflection. And again, back from the definition, it says that it's a point of inflection if it changes from concave up to concave down or concave down to concave up. So we're going to start by talking about the concavity, and then we will determine if any of the values that we found as being the intervals of concavity, where the ends of those intervals are, if those points are points of inflection. All right, so we're going to start by noting that this is continuous everywhere. It's also differentiable everywhere, and we need to find the second derivative. This one is lovely because it's just a plain old polynomial. All right, first derivative, 4x cubed minus 12x squared. Find the second derivative. We get 12x squared minus 24x. All right, for concavity, we find all places where the second derivative is 0 or undefined. Well, that's not a problem. The undefined part's not a problem here because there's no denominator that could make it undefined. So, as always, we want to factor this completely to help us find where it's 0. I'm going to take out a 12x, and I'm going to be left with x minus 2. And I want to know when that's 0. Well, it's going to happen when x equals 0 or when x equals 2. All right, so these are acting as the borders of regions where it could be concave up or concave down or something. So we're going to set up our intervals. And again, I'm just going to label these as possible points of inflection. Again, they are the borders of the intervals where the concavity stays constant in that interval. But we don't know if they're going to change from up to down or down to up. If they do, then they are definitely points of inflection. If they don't, then they're just interesting points. All right, so we're going to say our intervals are negative infinity to 0, 0 to 2, 2 to infinity. I'm going to pick a test value in there, so I'm going to go with x equals negative 1. And here I'm going to pick x equals positive 1. And in here I'm going to go with 3. All right, so let's talk about the sign of f double prime. So I'm going to use this factored form, the 12x times x minus 2. So in here we put in negative 1, we get negative, and then negative 1 minus 2 is negative. Negative times negative is positive. For the next section, I'm going to put in 1. 12 times 1 is positive, but 1 minus 2 is negative. So positive times negative, negative. And then here, I'm going to put in 3. 12 times 3 is positive. 3 minus 2 is positive. Positive times positive is positive. All right, so this is concave up. It's concave down in this interval. And in the interval 2 to infinity, it's concave up. All right, so what we want to see for it to be a point of inflection is at that point, at x equals 0 or at x equals 2, does the concavity switch, right? If it switches from down to up or up to down, then it is in fact a point of inflection. So I look at this, and an interval to the left of 0, it's concave up. In the interval to the right of 0, it's concave down. So yes, x equals 0 is a point of inflection. And then same thing here. If I look to the interval to the left of x equals 2, it's concave down. To the right, it's concave up. So x equals 2 is also a point of inflection. All right, let me show you what the graph looks like. And again, we're building up to the point where we're not going to need the textbook or our calculators to find the graph. We will find it on our own. So here's 2, and here is 0. Those are the values that we were testing. Here is what the graph looks like to the left of 0. Something like this. And then from 0 to 2, it looks something like this. And then at 2, it starts turning up like this. Again, I keep hitting the leg of my tripod, so I'm sorry about the wavy lines. But if I look at this, it's definitely curving up there, right? It's got an upward curve, so yes, this is concave up. From 0 to 2, notice how it's curving down. And then somewhere in this area, and specifically it's at 2, it's now curving up again. All right, so concave up. So here it's down. It's still decreasing, but it's not about whether it's increasing or decreasing. It's whether it's curving up or curving down. So right here it's curving up, and that then is our other point of inflection. So these two right here are where the concavity of the graph shifts. All right, let's talk about the second derivative test. All right, it says let f be a function such that f prime of c is 0. All right, so the first derivative is 0. The second derivative exists on an open interval around c. All right. If f double prime of c is positive, then it has a relative minimum at that point. And if f double prime of c is less than 0 at that point, then it has a relative maximum. Let's think about why this is true. All right, so we've got some point c in some interval, and we know that at that point c, first of all, we know that c is a critical value of the original function f, which means that most likely it has a horizontal tangent line there. Again, there are 3 different criteria here, so we'll see what happens. So assume first that it does have a horizontal tangent there. And it also tells us that the second derivative, the concavity, is positive, so it's concave up. So it has a horizontal tangent line and it's concave up. All right? That means that it has to have a relative minimum. All right? The other way we could assume is it does have a horizontal tangent line, but it's concave down there. Right? And that means that if this is a critical value, in other words, probably it's got a horizontal tangent line and it's concave down, then we know that it's a max. But remember, sometimes we said that not all critical values lead to someplace that has a horizontal tangent line. So it's saying if the second derivative at c is 0, the test is going to fail. All right? It's neither concave up nor concave down there. So it might be a relative max, it might be a relative min, or it might be nothing, all right? But if we can't conclude from the second derivative test, we have to go back to the first derivative test. And again, the first derivative test says that at c, you check values to the left to see if they're positive or increasing, values to the right to see if they're decreasing. If there's a change, then it is a max or a min. If there's no change, then we notice that it was going to look something like this probably, where it had a horizontal tangent line, but not because it was a max or a min. All right. I just have to say, for some reason in my mind, it takes me a while to remember this one. So please don't get too frustrated with yourself. Again, the first thing we need is all the critical values of the function. So where the first derivative is 0, And then we put those specific points in there to determine whether it's a max or a min. All right? Okay, let's do one more example. Oh, and then we're done. Yes. Okay, find the relative extrema for this. And again, they want us to use the second derivative test. So again, keep that page close by so that you don't forget. But second derivative test says first we need to find the first derivative and its critical value, specifically where is the function 0. So let's take the derivative of f, and we get negative 15 x to the fourth plus 15 x to the second. Right, so the second derivative test says find out all places where this is 0, and we're specifically going to look at them. All right, so I set this equal to 0, negative 15x to the fourth plus 15x squared equals 0. I take out a negative 15x squared, and I'm left with x squared minus 1 equals 0. Again, I want to find all places where this is 0, so I've got a product of two things equaling 0. So either negative 15 x squared equals 0, that leads us to x equals 0, or x squared minus 1 equals 0, that leads us to x equals positive or negative 1. Okay, so again, for second derivative tests, we're not looking at intervals, we're specifically looking at these points. What happens at these points? So I'm not going to say negative infinity to negative 1 and negative 1 to 0 and 0 to 1. I'm just specifically looking at these points. X equals negative 1, x equals 0, x equals positive 1. And I want to know what the sign of f double prime is. This is a typo right here. Should say f double prime. Okay, so I am going to plug f double prime in. I'm going to plug negative 1 into f double prime. So before I can do that, I need to find f double prime. Right? So the second derivative, all right, I'm going to get negative 60 x to the third plus 30 x. I'm going to factor out a negative 30x. So I'm going to get 2x squared minus 1. Let me just make sure I did that correctly. 4 times s. Yes. Factor on a negative. Yeah, okay. So I need to plug that into the second derivative and see what the sign is. So if I plug in negative 1 here, this is going to change that to positive. This is going to be 2 times 1, which is 2 minus 1 is 1. And so we end up with a positive right here. If I plug in 0, this gives me 0, so the whole thing is 0. And then here I plug in 1, I get negative 30, and here I'm going to get positive again. So this is negative. All right, so our second derivative test says that if we plug in the values where the first derivative is 0, we plug them into the second derivative, and it's positive, that means it's concave up, that means this must be a relative minimum. All right, again, if the concavity is positive, that means it's got to be down here at the bottom, it's got to be a min. Let's go over to this one. Here we plugged in one of the values that made the first derivative 0. We plugged it into the second derivative. It gave us a negative value, and that means it has to be doing something like this. It's concave down, so we're looking at a relative max. Here we plugged in one of those values into the second derivative and we got 0. The test fails. We can't tell from the second derivative test whether it's a relative max or a min. So we're going to say here, because the second derivative test failed for the point 0, 0, again, I got the second coordinate there just by plugging it back into the original function, we have to use the first derivative test. all right? And the first derivative test, again, just sets up two intervals, so that's negative infinity to 0 and 0 to infinity, and we pick a test value, so I'm going to pick negative, no, I can't pick negative 1, no, I can pick negative 1. No, I can't pick negative 1. I'm going to pick negative a half. I just want something just to the left of it and just to the right of it. That's our test value. And then I want to use the sign of f prime, and then I'm going to make a conclusion. I have to choose something that's, again, I know that there are 3 points where the derivative is 0, here, here, and here. So really I need to see what happens in here, right close to it. That's why I couldn't choose negative 1, because I know the sign at 0. I have to choose something really close to it. So I'm going to go with negative a half and positive a half. So I plug this in to the first derivative. I plug in negative 1/2 here, I get a negative value here, and I plug in negative 1/2 here, and I also get a negative value here, so this is negative. I plug in positive 1/2 here, and I get negative times a positive is negative, and I plug in a negative, or a positive 1/2 here, I also get a negative. So this gives me, sorry, this should have been positive. I don't know why I said that. It was negative times a negative, so it's positive. And likewise, I get negative times negative is positive. What that means is that on either side of 0, it's increasing. So it's going to do something like this. Increasing, increasing. It's not going to be a max or a min. All right, so the second derivative test failed. That means I had to go back and use the first derivative test. I get increasing, increasing. It is not a max or a min. So if the test fails, you have to refer back to the first derivative test, and this is what it's going to look like. All right, let me just give you a quick sketch of what the graph looks like right in here. I'm going to zoom back up here. At negative 1, it has a minimum down here. At 0, we already said it's nothing, and at positive 1, it's going to be up about here. So it comes down here, turns, it does something like this, and it increases, and then it decreases like this. All right, so again, concave up, the concavity is going to switch, well, somewhere in here. We actually didn't even find the concavity. We just found out that this was a minimum, this was a maximum, and even though this had a horizontal tangent line, it wasn't a max or a min. I wouldn't always use the second derivative test to find relative extrema. In fact, I feel like it's not that much more difficult to just use the first derivative, and then we only have to stop at the first derivative. So there are times where we'll want to use it, but it's not always the best thing to do. If it asked us to find more information like concavity or things like that, then I probably would have used it. But just for the first, to find out where we've got a max or a min, I would probably stick with the first derivative test. But here's an example of how it can be used. Okay, bye.